yes, I come from Fonterra, and you've already heard about Fonterra, and you all know about Fonterra, so I won't introduce Fonterra. And as Phil said, packaging is not all bad, and we know this because packaging is preserving food, which is super, super valuable. And it has a really strong functional purpose. But currently in industry, we're feeling a lot of pressure to improve the sustainability proposition of our packaging, right? And the key thing we can do as a person who packs food is to change the materials we're using to more sustainable materials. Unless you are extremely, extremely lucky, the functional properties of the sustainable, or the more sustainable materials are not going to match what you were using historically, and we need to be balancing our operations, balancing how we do things, and understanding what we can give and take on and where we can compromise. So that's what I'm going to have a little chat about quite quickly, and through two kind of lenses. And the first lens is talking about using recycle-ready packaging materials and balancing that against maintaining our product quality. I've got a couple of examples that I'll talk to, but they are just examples. It's sort of much bigger than just the case studies that I'm going to put to you today. I've just found the screen. It's over here. Okay, so example number one is a pouch for milk powder. You'll have all seen this, obviously consumed it. And I'm going to talk about how we make this run in the factory, right? We buy this as a flat sheet of plastic, we put it through what's called a form-fill seal machine, and we're going to form the back seam, we're going to form a bottom seam, we're going to fill it with milk powder, we're going to gas flush it, we're going to put a seal across the top, we're going to cut it off, right? That's how our process works. Historically, we've used non-sustainable materials, right? So they're a composite plastic material. On the outside skin, you've got something like PET. This is super simplified. It's very heat resistant, it's very stable, we can print on it. It holds the web stable when you're running it through your machine. There's a barrier in there somewhere historically made out of something like aluminium, really, really good barrier. And then there's a sealant layer. The sealant layer works, obviously, we put heat in when we seal this, and we melt that inner seal, right? When we move to a recycle-ready material, it's a little bit more like this again, very, very simplified. We've switched out the outer to some sort of polyolefin, we've switched out the barrier to something that's not aluminium, and we've kept that sealant layer. Now, our job in the factory is to keep this running and still make a good seal. If we don't make a good seal, if we don't put enough heat into that sealant layer, our packs will leak. The powder will fall out, or maybe the oxygen or the water will get in, both are bad. And we've done this by applying heat right through the bag. If we put too much heat in, what happens is our seals will all wrinkle up, shrivel, we might burn through if we're really unlucky. The key point here is that the traditional outer skin, the PET or the nylon or whatever we're using on the outside, if we switch that out to polyolefin, they're not the same. So I've tried to do a simple chart here, talking about how much heat we can put in before we start to get problems. So the darker blue bar is the historical materials we've been using, PET or nylon. You can put a lot of heat in there before things start to go wrong. The middle, the light blue, is the sort of heat we can put in when we switch out to a polyolefin material, right? A lot less tolerant to heat. And then in the grey, how much heat we need to put in to make that sealant layer form. And what you can see is there's not much gap between that grey bar and that little blue bar, right? There's a very, very small window to be able to operate successfully in the factory and make good quality seals. Often that window is so small we can't actually process these materials. So this is something that we're working through at Fonterra, and I'm sure lots and lots of other people are working through as well. How do we make this so that we can continue to make good packs? There are some technologies that we can utilise, right? There's continual investment by the plastics people to make more heat-resistant films or heat-resistant lacquers on the outside, right? So we can improve heat resistance. There's also highly likely a need to modify sealing equipment, so to change the profile of those sealers to get a better outcome, or maybe change sealing mechanisms altogether to something like ultrasonics. What we have to do is do this for every packaging material on every production line. It is a long, slow changeover, right? Everything has to be evaluated because every line runs differently. Good. Next example, changing a little bit now. We've got a big block of cheese. Now this particular cheese we pack it into this plastic bag and we put it through a hot water bath to shrink it down so it forms this skin-tight pack around our 10-kilo block of cheese. We then mature the cheese inside that bag, and then we ship it off to our customers all around the world in that same bag, right? And it's important to our customers that this is skin tight when they get it. If it's not skin tight anymore, they will associate that with microbial spoilage. What's happening when we mature the cheese, which I've represented with a yellow cheese thing, when it's inside the bag, is that it's maturing and it's producing gas, right? That's where the little eyes in cheese come from. It's carbon dioxide gas. It needs to get out of that bag. But we don't want to let oxygen in, because if we let too much oxygen in, we'll grow mould, and nobody particularly likes mould in their cheese. The materials we've historically used in this kind of packaging for a barrier rely on PVDC as a barrier. And PVDC is really cool because it's got a really, really good barrier to oxygen. It keeps that out, but it's really quite leaky to carbon dioxide. It'll let the carbon dioxide out again. It's really good. It's not recyclable. So we have to switch out the materials, and the most common barrier in this application would be to switch to something called EVOH. EVOH, unfortunately, is really good. So it'll keep out the oxygen, it'll also prevent transfer of that carbon dioxide. It will trap that gas in the bag, which is actually not what we want. I have, fingers crossed, a little video that shows when you get a little bit of gas in the bag, start to get a little bit of a trampoline. I just put that in because it's cool. So how we solve for this, right, is that we utilise, and this is not just obviously for this cheese product, advances that the plastics people are making in barrier technologies, right? They're playing around all the time with different technologies that we can utilise. We also absolutely have to understand the product and the supply chain conditions, because we can't necessarily do what we've always done. We can't match the barrier performance that we've always had, so we have to understand actually where our thresholds and our limits are. We have to do this again, every product. Right? We have to understand stuff that we've maybe never had to completely understand before, so we know where our tolerances are and we can design the right packaging for it. Cool. Change angle again. Another thing we can do to make our packaging more recyclable is use recycled content in that packaging, right? This closes the loop. You make it recyclable, somebody recycles it, then you use that recycled content again. We have to balance this against ensuring food safety. Cool. So I'm going to not talk about the hazards that might be in recycled plastic, because I'm quite sure somebody else is, but I'm going to very quickly talk about the technologies that are used to recycle plastic, okay? So in here, basically, right, recycling plastic is about taking old stuff that's been used, cleaning it up, using it again in food packaging. The cleaning it up bit's really quite important, as you can well imagine, right? And there are different ways we can do the cleaning it up bit. We can do quite a small loop. We can do a plastic-to-plastic mechanical recycling loop. We can take plastic, chop it up, heat it, extract the volatiles, use it again. We can not do that. We can, if we want, go plastic to polymer or plastic to monomer. We can apply what's, some of these chemical recycling technologies. We can start to play with the chemical bonds, right? Break the chemistry down a bit more, be able to extract more additives out, be able to depolymerise things. You won't have heard, probably many of you, many technologies in this space. There's not much going on commercially in the world in this space, only very small applications for this. And then we take the biggest loop you can get, which is complete thermal decomposition plastic, right back to oil or right back to gas, right? And you will have heard the word pyrolysis. This is one of the technologies that you can do in this space. You might have heard of thermochemical liquefaction, because there's been talk about that in New Zealand. So this, we're taking it right back to oil. It is going to go then into the front end of a refinery in the petrochemical industry and go through all the processes to turn back into plastic again. As a general rule, and again, massively simplified, as we move along this, which is in that direction, food safety gets better, general rule. Technological performance gets better, general rule. Cost goes up, carbon footprint goes up, right? So we're not all going to immediately leap to the far end to complete thermal decomposition, because it's not solving for cost, it's not solving for carbon footprint, and to be fair, it's not solving for all of the different plastics that we use either. Only some can go into that system. So what we're doing is juggling, is trying to balance how far up the spectrum do we have to move to get to that sweet spot that we need to be operating at. And the reason why I talk about this one today is because it's different to my other examples. My other examples, you had to understand a process, a line, a product, and go through it. Fonterra has to go through this sort of line by line by line, right? This is not something that we do in that way. This is not something we can understand where to play, line by line, company by company. This is something we need to do collectively as an industry, right? The solve looks very different. And it's also, I guess, no longer an option as well, right? So we know that there are regulations coming in that are going to require the use of recycled content. The packaging and packaging waste regulations in Europe is an example of that. By 2030, all packaging going into Europe has to have some amount of recycled content in it. This is not optional, right, for exporters. So, given that we need to work collectively on this, I thought I'd share my view on what collective might look like in the New Zealand space. And I've got down the side, this is my most complicated chart of the day, it's also my last slide. In simple terms, the major kind of recycling processes that we're talking about, right? The top one, complete thermal decomposition, so pyrolysis kind of stuff, right? Now you can see in the New Zealand context, we would source this from offshore. It's not something we don't make plastics in New Zealand, right? So we cannot do this whole cycle in New Zealand. And we would typically be using this for polyolefin, so polypropylenes, polyethylene, right? From a food safety perspective, it is considered equivalent to virgin, so that's a really great tick. In terms of market access, we think there's no bans. To be fair, there's a couple of markets like China that are silent on this, but we also know this is indistinguishable from virgin, right? So logically, there's no way you could make a ban on it, but China has been silent on it, so we need to be careful. And in terms of market access, in terms of food contact compliance, we follow the same rules as virgin. So actually no job to be done, except for those of us who have to source that recycled content and get it into our packaging for Europe. No particular sort of industry solve needed here. The next one down, mechanically recycled PET, and I specifically call out PET as the reason that I'm talking about here, right? We can source this already from New Zealand or from Australia or further afield. And it is used specifically, obviously, for PET, for rigid PET, for trays and bottles. That's the only place this plays out. Food safety perspective, it is well proven. It's got 20 years of history, right? If it's well controlled and it is known what those control measures need to look like, food safety is, sufficiently de-risked. Market access bans, there are some. China won't allow this through the door, Malaysia won't allow this through the door, right? There are probably other markets. So that's important if you're an exporter. And food contact compliance, what's also really important is that most of the countries that allow it in have specific regulation in the space that has to be followed. So case in point would be EU. So we've already said EU is going to require the use of recycled content by 2030. They've also got regs that say what that has to look like. They have a particular regulation, 22/16/16. We, as New Zealand, need to work out how that plays out and how we can make sure that we comply with this if we're exporting into Europe. The last bit is anything else. Any other process at all falls into my anything else bucket, right? That would include mechanically recycling something that is not PET. Or it would include some of those dissolution kind of processes in the middle of the chart I showed before. Again, we source these from offshore. And the major use probably is for rigid packaging, right? They are all relatively new processes, so we may not yet know how to control these well enough to mitigate that food safety risk to a place that we're all comfortable to use this in the food industry, right? There are lots of countries that don't allow this, so the list you'll notice has expanded significantly. And again, same rules has to be, meet food contact compliance. And again, case in point, Europe, EFSA haven't yet authorised anybody in any of these processes. So what we need to do in New Zealand, again, understand this space. If we're going to be using this recycled content, we need to understand what we need to do firstly for food safety domestically, and then secondly to ensure we don't have market access problems. Was that my 15-minute cough, Phil? That was subtle. Thank you.